Okay, this is exam 4, physics 202, spring 2014. A positively charged particle enters this magnetic field. What's the force acting on it? Okay, well, our velocity is down, magnetic field, so that means that the force here is going to be out of the page. Velocity is down, magnetic field, fingers in the direction of velocity, magnetic field comes out of your palm, thumb points out of the page, so that's B. Which of these statements is true? Magnets have only a north or south pole. That's not true. That would say it has a monopole. North poles attract. That's not true. They repel. And wood is not ferromagnetic. None of these are true. Mass spectrometer looks like this. What is the direction of the initial force on a particle? All right, well, this is similar to what we had before, but here I have a velocity in this direction. My magnetic field is in that direction, and so the force is down. So this particle is going to follow a path that looks like this. Magnetic pole of the Earth nearest the geographic North Pole corresponds to the magnetic southern pole. Let's see. Positive charge approaches this wire. What is the direction of the current? Okay, well, in order to follow this path, I have to have a force that's in this direction. So that tells me that my magnetic field, if I let my thumb go in the direction of the force, my velocity is in this direction, my fingers go in the direction of velocity. The magnetic field has to be into the page to cause this current, or this direction. And then I use my curl rule, let my fingers wrap around to give the magnetic field. The current has to be to the right in order to cause that. All right, which of these statements is true? All right, I draw my wave fronts here. It has to slow down in order to cause this type of refraction, this bending. So if it slows down there, that means that N2 is bigger than N1 RC. What is the angle of reflection from mirror 2? Well, let's see here. So I get an angle of 50 degrees here. That means this is 40 degrees, 40 and 60, so this has to be 80 degrees. So if that's 80, this incident angle is 10 degrees, and so the reflected angle is also 10 degrees. Organize these in terms of shortest wavelength to longest wavelength. That means also from highest energy to lowest energy. So that's going to be gamma, ultraviolet, visible, and radio. Gamma, ultraviolet, visible, and radio, that's A. Newton explained light as a particle because of reflection. Huygens described light as a wave because of refraction. The index of refraction is dependent on wavelength. When a white light passes through a prism, which color will be bent or refracted the most? Okay, well, first of all, you want to recognize that this is blue, this is red, is long wavelength. So refracted the most will be the light that has the highest index of refraction, so that's going to be D. Okay, I had fewer multiple choice problems on this question. All right, what would happen, first of all, if the cladding had an index of refraction higher than that of the core? Okay, in this case, there would be no total internal reflection. Because when the light comes up to this, instead of bending away from the normal, it would bend towards the normal, and the light would escape the fiber optic cable. All right, what is the angle subtended by the acceptance cone? We had a homework problem very similar to this, a practice test problem very similar to this. Here, I have a light ray. It comes in like this, and then it bends. All right, I want to find this angle. I'll call it phi. And then the cone will be twice that angle. The acceptance cone will be twice that angle. All right, so first of all, I want to find out what must this angle be in order to get total internal reflection. So in order to do that, I say N1, that's going to be 1.5 sine of theta C equals 1.2 sine of 90. All right, this, of course, is 1. And then I can calculate my critical angle. It's going to be the inverse sine of 1.2 or 1.5. And that's 53 degrees. Okay, so that critical angle is 53 degrees. That means that this angle equals 90 minus 53. That's what, 37 degrees. All right, if that angle is 37 degrees, this angle is also 37. This angle then is 53, and so this angle is 37 degrees as well. All right, so that angle is 37, and now it becomes a simple refraction problem. Now I have this light ray that comes in. Let me redraw that just a little bit. I have a light ray that comes in. And it bends towards the normal like this. All right. I know that this angle is 37 degrees. What I'm drawing here is this scenario, and I want to find out what is phi. All right, so I have, so let me go back up again. This n is 1.5, this n is 1. So I say 1 sine of phi equals 1.5 sine of 37. And then I solve that for phi. I get 65 degrees. All right, that means that the acceptance cone for the angle theta is going to be twice phi. That's 130 degrees. So that angle theta will equal 130 degrees. Okay, now for 3, what is the speed of light within the cable? Well, within the cable, n equals 1.5. So v is equal to c divided by n. That is going to be 3 times 10 to the 8th divided by 1.5. So it's 2 times 10 to the 8th meters per second. That's the answer. And then estimate time required for light to travel 1,000 meters. All right, well, this is just going to be v equals d over t. And again, I said to assume a straight line path. You know, in reality, light sort of bounces back and forth. So even though it's the cable is 1,000 meters, the light is actually traveling slightly further than that. Now, the cable is very narrow, so it's not really that much more than 1,000 meters. Anyway, I calculate my time here, d over v. 1,000 meters over 2 times 10 to the 8th. So it's going to be 500 times 10 to the minus 8 seconds, or however you want to express that in decimal form. Okay. It's not very long. Okay, this is a mass spectrometer problem. So first I want to know the unknown particle, R equals mv over qb. That's the cyclotron equation. M over q equals r b over v. Let's see, r is 0.5 meters. B is 2 Tesla. And v was 2 meters per second. Now, given these numbers are not realistic, obviously, these a 2 Tesla magnetic field is quite large. A 2 meter per second speed is quite large as well, or quite small rather. So I just did this to make the numbers quite easy. So a mass charge ratio of 1 to 2. Now I want to find which of these has a mass to charge ratio of 1 to 2. All right, here we go. 1 to 2, 2 to 1, 4 to 1, 3 to 1. So delirium is the right particle. Now B, what is the magnitude of the electric field that must be applied to the charged particle so that they move in a straight line? All right, so here I have this particle that is traveling in a curved path. It has a magnetic field acting to give it a force. So it has a magnetic force equal to QVB. That's going to be the charge rather, which is 2 coulombs. So 2 coulombs times 2 meters per second times 2 Tesla. So it has a magnetic force equal to 2 times 2 times 2, which is 8 newtons. And so the electric force is also 8 newtons. And don't forget the electric force is equal to Q times E. And so E is equal to 8 newtons over Q, which is 2 coulombs. That's 4 newtons per coulomb. And then how does a mass spectrometer work? Well, an unknown particle or an unknown substance is vaporized, ionized, accelerated, and accelerated through a magnetic field. Okay, sorry about that. Accelerated through a magnetic field, and then you measure the radius of the path to calculate the mass to charge ratio. See, that should be good. 3, 4, 5, 6, 7, 8. That's about less than 20 words. All right. Vaporize, ionize, and accelerate through a magnetic field, and then you measure the radius of the path, just as we've done. Okay, this loop of wire is current of 3 amps, sits in the uniform magnetic field as shown. Give the force on the left-hand side. So I want to know the force on this side. First, let's just express L in vector notation. Let's see here. I'm going to draw this as a triangle. This is 1.41 meters. This is 45 degrees. So this side is going to be 1.41 cosine of 45. And this is 1.41 sine of 45. And you'll find that the vector notation of this is going to be negative 1I minus 1J. All right, it's negative because I have a negative quantity there and a negative quantity there. I guess that angle's more than 45 degrees. But anyway, you get the idea. So it's it's negative because my y component is down and my x component is down. Now for this right-hand side, the x component would be positive and the y component would be positive, which would just give you a force that's in the opposite direction as we've talked about before. All right, so if I want to know the force, F is equal to IL cross B. That's going to be 3 amps times negative 1I minus 1J crossed with the magnetic field, which is 2I. Right, this is pretty simple. 3 amps. This portion equals 0 because it's I cross I. So I get negative 2J cross I. And so J cross I is negative K, where you can do your right-hand rule. Fingers in the direction of J, pull towards I, or palm in the direction of I, gives you negative K. So this is positive 6K. All right, so that is the force, positive 6K on the left-hand side. And so if I label that, notice that it is positive. So that force is going to look like that. On this side, the force will be into the page. Right? So that's going to cause this loop to turn. And then what is the magnitude of the net torque on the loop? All right, so torque equals F perpendicular times the radius. The radius of the motion is just, or the moment arm is just that distance, 0.1 meters. And I know the force now is 6 newtons times 0.1 meters. So the magnitude of the torque just due to that one force is equal to 0.6 Newton meters. But the total torque is going to be twice that. So the total torque, which is the torque on the left-hand side plus the torque on the right-hand side, will be 1.2 Newton meters. And I said to disregard the forces on these small ends. They do experience a certain amount of torque, but it's small compared to the torque that's experienced by these long ends. All right, I think there's one more. Yeah, this was just simple cross product. F equals QV cross B. 2 coulomb charge. V is 2J minus 3K. Crossed with a magnetic field of 10I. Right. And again, these numbers are not realistic. I've just used easy numbers to make it easier for you. Right, so I have 20 J cross I minus 30 K cross I. And do your unit vectors, I, J, K. You find that J cross I, if you do your right-hand rule, or if you just remember this or whatever, it's equal to negative K. And then K cross I, what is K cross I? K cross I is positive J. And so this is going to be 40 times J cross I, which is negative K, so negative 40K. And then K cross I is positive J, so minus 60J. That's in newtons. So that's the answer. And there's the answers to the multiple choice.